Well, welcome back to the Simon Center, and we are waiting for Steven and Pam de la Pietra, but we think that we cannot let you, wait a little longer. As usual, we are really grateful to the de la Pietra families, Barbara, Steven, Vincent, and Pam, for the constant and unwavering support that they provide to the outreach activities of the Simon Center and also at large to many activities at the university. So we're really grateful that they continue supporting all the stuff that we do here. And this is one more event, one of these more series in the De La Pietra lecture. We have Cumrun Vafa, which is one of the major pillars in string theory for the last few decades. He has all kinds of prizes that you could imagine. You can look it up on the web. But for us, one of the important things is that somehow trying to bring Cumrun to Stony Brook in the 90s and early 2000s is what really is at the root of this center. Cumrun and Martin Rocek started the summer workshop in theoretical physics in 2003. It's been running almost uninterruptedly for 19 years. And somehow this is what inspired Jim, and of course many other people participated from the YITP and the math department, to eventually create this center. So in a sense, not only he's a great scientist, but he's also first the person who inspired to create this place. And also, he joined the board of trustees, and he's been working and helping us inspire and structure the programs and the science of this center since its very beginning. So we are extremely grateful to Cumrun for all the work and the effort that he spent in helping us at the center. And now we're going to exploit him a little more. Because I think, apart from just participating in some of these boring meetings, now he's going to become an entertainer. And then he's going to give us a very nice lecture on these puzzles to unravel the universe. Please, Cumrun.
Thanks, Luis, for such a kind and warm introduction. I'm not so sure how good entertainer I am, but at any rate, it's always a pleasure to be here. But this one in particular, to be here in recognition of this lecture series of De La Pietra families who are good friends from decades ago. We won't say the exact date or anything. And also the topic that I have chosen is related to the topic that I cherish a lot in discussing with them, which are puzzles. The only drawback is that they have heard all of these puzzles in some form, so I apologize to them specifically, but here we go, and I'm going to talk about this topic. So there are many deep physical ideas that have simple mathematical underpinnings. And the simple truths that are there in the physical laws is what we're after, really. When we talk about physics, sometimes it gets complicated, looks like complicated mathematical formalism, but we are looking for these nuggets of truth, really, these simple points. Nothing too fancy, even though it might sound fancy to the uninitiated. We're not interested in that. We're not trying to impress. We're trying to get to the bottom of these simple ideas. And sometimes this gets lost when we try to explain what we are doing to people who are not physicists or mathematicians. Now, it turns out that sometimes puzzles, simple mathematical puzzles, get to the depth of these nuggets of truth without the cloudy part on the peripheral things which are irrelevant for the basic issue. And the puzzles are fun in their own right, but they're also interesting to try to nucleate, to get to this simple fact in a simple, fast form and explain it to people who are not necessarily physicists or mathematicians. So the idea that you can describe deep connections between physics and math and the basic principles that underline the physical laws using puzzles was related to a freshman seminar that I started at Harvard since 2012, about 10 years ago. And the course has grown organically by the puzzles that students bring to the class. And so that's basically how this whole thing emerged from a freshman seminar course at Harvard. And it led to a book that I put together based on these lectures that I gave in the freshman seminar. COVID time was a suitable time to sit down and put it together. So that's when the book came out in the pandemic period. And I'm going to talk about some aspects of some of these puzzles. So math and physics have had a beautiful history of interaction over thousands of years. And so perhaps some highlights from the past might be suitable to remind us of this connection. Greek mathematicians and philosophers were talking already about the connection between math and geometry and how it could be possibly related to nature. The 5 elements, air, earth, fire, the universe, and the water, they were connecting to Platonic solids in some form, and they were trying to connect nature in this form to symmetries or symmetric objects like Platonic solids. So that idea that geometry or symmetry is related to nature and forces and so on in some form was already millennia, thousands of years old. It's not new to us. The connection between mathematics and science developed by different cultures over different periods, by Chinese scientists and mathematicians, by Indians, and also by Islamic scientists. And there were interesting, simple things that came out of some of these. For example, originally the ideas were just in some form, just using simple mathematics to get to some simple points. For example, can you measure the radius of the Earth? The Greeks already had one way of doing it by looking at the length of the shadow and how that changes when you go from the equator up along towards the north. But there are other ways, for example, by measuring the height of a mountain, looking at the mountain and looking at the angle that the horizon makes and so forth with respect to the vertical line and so forth. Using these kind of simple ideas, people could measure, like Biruni did, for the height of the radius of the Earth. But there was actually more amazing things they did using simple mathematics. Like, we think, only recently we have measured that there is an atmosphere and what is its height. It turns out that about 1,000 years ago, scientists had already measured the height of the atmosphere, remarkably, and using simple ideas of geometry. And this involves simply the point that if you are, let's say, over here, and if you see a sunset, the sun goes down, you won't see the sun, but the sky above you doesn't get dark immediately. It takes a while, and the reason is that they hypothesize that must be that the sun is still shining some upper parts of the atmosphere, and if it goes too far down, then it won't even get to the upper atmosphere, and then the sky is totally dark. So the time it took between the sunset to the full darkness was a measure of the height of the atmosphere, and that they used to, for example, come up with a simple formula trying to explain that. So these simple ideas were just the beginning of trying to use geometry and trying to do measurements or trying to understand how the things around us fit together. But this got much more advanced by Newton's work, in particular in the context of calculus and the laws of mechanics. That was a breakthrough which really brought new mathematics even to describe physical phenomena. Later, mathematicians who were interested in some physical things, they came up with ideas purely from mathematical motivation, but the ideas that was kind of around was that the idea of Euclidean geometry that we were using in physics was not the only kind of geometry that was possible mathematically, and raised the question of whether or not our universe has something to do with geometries other than Euclidean geometry. It's the legend, perhaps, that the validity, I'm not completely sure, but it was said that Gauss, for example, would go on top of the mountains trying to look at the other tops of 2 other mountains and trying to look at the direction that he sees the other mountains and the angles that they make, whether they sum up to 180 degrees, and in other words, whether you have a Euclidean geometry or not. Of course, if he did that, he would fail to see it because it was so tiny it wouldn't be measurable by his methods. But at any rate, the idea that geometry or mathematics leads to a question is natural in this context. And other example is Maxwell's development of electricity and magnetism, which is captured by differential calculus through the beautiful equations of Maxwell, which, to make it consistent, he had the terms which led to the existence of waves of electricity and magnetism, which he identified with light. Again, this was really just tour de force of trying to make sure math is consistent, and that led him to the discovery that the proposal that the light is nothing but electromagnetic waves moving. And again, now the Riemann came along and he talked about geometry, and he was very interested actually in physical concepts, and he was really interested in trying to apply Riemannian geometry, the geometry of trying to describe the manifolds of higher dimensions and different kinds of metrics and so forth, connecting it to the physics. And he was a little bit ahead of his time in that application. He was trying to do something that the basic tool was not there in the language that Einstein brought in, is to combine space and time together. And Einstein used Riemannian geometry in the context of 3 spatial dimensions and 1 time, combining them. And he wrote his beautiful equations, which captured the response of space and time fabric geometry to putting matter around, and how, for example, sun and stars or Earth, etc., get to curve the space around us. So again, the deep connection between physics and geometry. And then Kaluza and Klein, using Einstein theory in yet one higher dimension, going from 3 to 4 dimensions, spatial dimensions, in 4 + 1 dimension, tried to use this setup to combine gravity and electromagnetism by going to higher dimensions. So this geometry was trying to be used in some form to unify physics of forces that we knew, gravity and electromagnetism. So these were some of the ideas that were kind of around, and this brings us more or less to a situation that which is happening now, which is my area of research, which is called string theory. And the aim of the string theory is to unify fundamental forces and particles into one framework. It aims to describe physics from the smallest, tiniest scale to the biggest one in one uniform setup. And the basic postulate is that fundamental particles are not point-like, but extended objects like strings. So we think about objects like quarks, which make up a proton, as actually at a smaller scale to be entities like strings that we cannot discern as strings because we cannot focus, we cannot zoom in as much to see it, because the size of these strings are so tiny, it is hard to discern. The main point about string theory is that it resolves an inconsistency between 2 pillars of physics, quantum theory and Einstein's gravity. And that's why we believe in it. So basic structure of forces in string theory is simply described by this simple picture that 2 strings come and join, or going backwards, the string comes and splits to 2 strings. And this is, in the context of string theory, captures all the interactions between all forces, and different excitations of strings will correspond to all the different particles we see, and some that we haven't even seen yet. So this is the kind of a unification of forces, of particles, and the geometric picture of describing all the forces into this simple picture, like what we call pairs of pants diagram. As you can see, looks like a pair of pants. So this area is very mathematical, string theory, and it involves many abstract ideas. The dimension of space is more than 3 + 1 in string theory. In fact, it's 9 spatial dimension and 1 time direction. And the shape and size of the other tiny 6 dimensions affect what we see in our universe. So the details of these 6 dimensions are crucial in telling us what we are going to see. They are assumed to be tiny, otherwise we would have seen it by now. We don't see the extra 6 dimension, and part of the hypothesis is that they are so tiny we cannot see them easily. Strings wrapped around these tiny dimensions lead to insights about, for example, how black hole works and how the beginning of the universe may look like, etc. So we think about it like this: at every point in the macroscopic space, the 3 spatial dimension, you can imagine these tiny spatial directions that are like spheres or something even much more complicated than the sphere, which are there. And they're so tiny, we won't be able to see them in everyday experiments. We just average over them in some sense, and we just see the macroscopic directions. So the aim for my talk is not so much to review string theory, though. And the aim is different. My aim is to show that, well, to give examples that some of these highly mathematical aspects of theories like string theory can be exemplified by simpler ideas, and these ideas are simple puzzles that I want to use to illustrate some basic features. Needless to say, these are just illustrative points. It's not going to be that I can cover all the principles of string theory, for example, using these puzzles. No way. But I can certainly try to give a flavor of some nuggets of truth in the sense of connections between physics principles and math puzzles and mathematical ideas. So the first topic I want to talk about is symmetry and conservation laws. So I'm going to describe puzzles, and I need your help in solving it. So I might ask you questions, and you may, if you wish, answer me by raising hands. I would say yes or no in such a way that you can raise your hands. So the first topic has to do with symmetry and conservation law. We have two buckets of paints. One is green paint, and one is white paint. We take some of green paint, a certain amount of it, and pour it into the white paint. We stir it well. And then we take the same amount we put into the white and put it back into the green paint. And also stir that. Okay, good. So now we have mixtures. One of them is mostly green, the other one is mostly white. Okay, so far so good. So the question we want to ask is, which container has a higher concentration of the other color? Does the green have more white in it, or white has more green in it? Now, those who think that the white has more green in it, raise your hand. Those who think that the green has more white in it, please raise your hand. Okay, very few, okay. Those who think they are equal, raise your hand. Okay, very good. So now, I would say that among the first two alternatives, most people chose that white has more green. And I think that is the most intuitive answer, perhaps, and that's the one I would have given. And the reason is kind of like, look, originally you're taking a full, pure green and putting in the white. But when you mix it, you are getting some of the mixture of the white and green back to green. So, therefore, the white will have more green in it. That's the natural intuition. Okay, so that kind of intuition might lead people to think that the white has more green than green has white. But actually, the answer is that they have the same amount. And this has to do with the simple idea of conservation and symmetry in this case. And I want to say why the symmetry and conservation in this case will lead to that. First of all, notice that the amount of volume of these paints are set amounts. Total amount of the green and the white are equal to begin with. And at the end, the greens don't disappear. They can relocate from one container to another, but they don't disappear. And the same with the white. And there's a symmetry between them, between the containers. They are equal in size and so on. So if you think about it, and if you kind of think about unmixing them, you must have the same amount of the green in the white and the white in the green, because the total volume is the case, and you can swap them back so that it will go back to the same amount. If one had more than the other, you would have broken the symmetry between them. So it's simply a symmetry and conservation argument here. There's nothing complicated, but it deconfuses us because the intuition would lead us incorrectly to think perhaps the white has more green in it. Yes?
Still true.
Yes, that's true. That's true. So conservation is, in this case, I'm using symmetry, but you can actually relax that part, but conservation will be what you'd need. Conservation of mass. So that's the first puzzle. Let's go on to the next one. Aristotle famously thought that heavier objects fall faster to the ground. Again, it's intuitively natural to think that way. You have a heavy stone, you have a tiny pebble. You forget about the tiny pebble, you're worried about the heavy stone. You think that's falling faster and so on. So that's natural to think the heavier objects fall faster. Galileo said, no, all objects fall at the same rate. How did he do that? He experimented. It said that he went to Pisa Tower and then he dropped different sizes stones and so on, and he checked that no, they all fall at the same rate. Okay. Now, it is said that the scientists at his time did not agree with his analysis. Experiment was not enough. They told him, experiment? No, you have to explain why such a thing would be true. At that time, science was not as experimental as it is today. It was kind of like you have to kind of explain why it had to be that way or something. In other words, you don't have to mess your hand with the experiment to come up with the fact. It was kind of that kind of mentality. So Galileo had to come up with more than experiment to convince people, the scientists that in his period, that actually there's a good reason for this. What is the reason for that? And he did a simple kind of a symmetry argument. His argument was the following. He said, suppose we have 3 bricks and we drop them to the ground at the same time from the same height. Well, they will hit the ground at the same time, obviously. Why? Well, there's a symmetry in this situation because you can translate horizontally the brick from one to the other, and the bricks are exactly the same mass and shape and everything. So there's no difference between them. So by simple translation horizontally, you replace one brick with the other. So if you replace them at the same time, it should fall at the same time. So symmetry argument naturally leads you to think they should fall at the same time. So everybody says, yes, of course, we know this. This is trivial. Give us something more interesting. Then Galileo says, okay, suppose I move the bricks a little bit horizontally in one way or the other. Would it change the answer? They would say, of course not. Why should it change the answer? Because if you move them, as long as they're the same height and you release at the same time, again, you still have that symmetry that we talked about. Said, okay, so if you move them a little bit closer and closer, does it change it? They said, no, of course not. Okay, what's next? Said, okay, suppose I move them so much that they're actually, 2 of them are actually touching and do it. Does it change it? Said, no, of course not. Why should it change anything? Said, that's now twice bigger than the other one. And you're saying that combination of those 2 bricks fall at the same rate as the other one. So again, this idea of symmetry can deconfuse us about something that's so obvious to the naive mind, that the heavier object falls faster than the lighter object. Many examples of this is the analog of what we could call Gedanken experiment, even though in this case you can actually do it very easily, appears again and again in different physical contexts. For example, in Einstein's development of his theory of relativity, in that case, he was imagining, on a train with a speed close to the speed of light and so on, which you cannot realize pragmatically. But it was a very useful way of thinking to try to convince people about how the thing works. So this is a very typical situation in physics. Now, even though symmetries are fun, more fun is breaking them spontaneously, automatically by themselves. So here is the puzzle. We have 4 towns, A, B, C, and D, on the 4 corners of a square. And we want to design a highway system which connects all these 4 cities together. We want the total length of the highway to be the shortest possible, the total length. It doesn't matter if you can directly go from one city to another, as long as you can get from any city to any other city, that's fine. Is the question clear? The question is, design this highway system. How many of you think this is the answer? Raise your hand. How many of you think this is the answer? Raise your hand. Okay, so most of you think neither of them is the answer. Good, okay. Okay, so in fact, this cannot be the right answer in an obvious way, because you can even remove one length, and you can still get from one to the other. In fact, you can move this around the other line, it still works. It turns out this is the answer. Now, this is a bizarre answer, because first of all, these three angles are 120 degrees, and so you have this bizarre shaped highway system. And there's something unintuitive about the answer. The thing that's unintuitive, perhaps, is that you started with something which looked like square symmetries, but the answer does not respect that, which means what? It means, suppose you want to go from city A to city B versus going from city A to city C, you can get much faster from A to C than from A to B, because that length is longer, even though they are both on the corners, adjacent corners of a square. So that's strange. So in other words, we say that the highway system breaks the symmetries of the square. It doesn't have the symmetry we started with. So the answer came here by trying to find a highway system which minimizes the total length. Of course, there's another solution. We can go the other way, but that one also breaks the symmetry. So either solution you choose will break the symmetry of the square. Another example of symmetry breaking, just to make sure that this idea is not new. This idea was known to Greek philosophers. You see, they had already, these Greek philosophers are very smart. They had already figured out that Earth is round, and they thought that it's at the center of the universe. And it's not moving. It didn't seem to move. They were looking at the moon and this and that moves, but Earth didn't seem to move. So they were a bit puzzled why all these objects are moving around them. And they had figured out that the Earth is probably round, but the Earth is not moving. What's the story there? Well, they came up with an amazing idea. They said, suppose Earth is at the center of the universe, and suppose it were to move. What will happen? Well, it has to pick a direction to go. If it does that, it breaks a symmetry. You have to pick a direction. So they say, this is not good because breaking symmetry is not allowed. Center of the universe, Earth stays there because each direction it chooses, you break a symmetry. That's not going to happen. So this was an argument which sounds very modern, because in modern days we use similar arguments to use the power of symmetry. And they were trying to use the argument of symmetries to prohibit the motion of the Earth, because any movement in any direction will break that spherical symmetry. But there were actually other people among the group which were even smarter. Aristotle did not accept this argument. He said it's not a good argument. Why didn't he like the argument? He said, well, suppose you put a person at the center of a circle and spread food around the circle, equal distance to the person, and tell me what's going to happen. Do you think the person is going to stay there forever? Absolutely not. He's going to go somewhere. He's not going to starve. So you say he breaks the symmetry. He says, yeah, you break the symmetry to get the food, of course. So we do break the symmetry sometimes if it's convenient. This is an example he gave. This picture is so close to the modern day mechanism, what we call the Higgs mechanism, which gives particles masses, which is amazing. It's remarkable that this is so close to this way of thinking. Was already there a few thousand years ago. In fact, symmetry breaking is in our bodies. Look, our eyes are not around in a circle, even though we live in an environment which is almost circular symmetric. Our eyes are in the front, not all around our heads, which you would have thought by symmetry should have been like that. Why? Well, evolution chose it that way. Evolution decided that the resource of putting eye in the front direction is more useful than spreading it all around, given the limited resources available. And why did it do that? Well, probably for the same reason Aristotle pointed out. You want to go after the food. You see where the food is and you go after it. So motion might be related to why we have broken that symmetry in our body. In fact, there's an evidence for this, because if you look at trees don't move, and typically they are more symmetrical. So in some sense, this is kind of relating a pragmatic mechanism of breaking symmetries with optimizing some situation, and this is already in our own bodies. So spontaneous symmetry breaking has many applications. I mentioned one, the origins of mass, what we call the Higgs particle or Higgs mechanism, which is very much similar to the picture that Aristotle was getting about that bread example. Why there is more matter than antimatter. In the early universe, you might have thought that there are equal amount of matter or antimatter, but there's this tiny asymmetry, 1 in 10 to the 9, 1 in a billion, and we think that the matter and antimatter annihilated almost perfectly, except this 1 in a billion survived, and that's what we are made of. So that asymmetry, spontaneous symmetry breaking, is related potentially to the existence of matter. Magnets, existence of ferromagnets is another example of spontaneous symmetry breaking. And superconductors is another. So all these cool examples are not because of symmetry, but because of spontaneous symmetry breaking. So these are some of the simple examples I want to give about symmetries and the breaking of the symmetries. So now I want to move on to the power of simple and abstract math. So consider Earth on the equator. So this is the equator. And imagine that you have wrapped a belt around the equator, and you open it up, from this big belt here, and somehow you are allowed to add 1 meter to it over at the end, this 1 meter. And you wrap it around the Earth again. Now it's going to stand a little bit above the Earth. Right? So the question is, how much does it stand above the Earth? What is x? How many of you think it is half a meter or more? Raise your hand. How many of you think it's a centimeter or more? Raise your hand. How many of you think it is a millimeter or more? Raise your hand. Okay, how many of you think it's sub-millimeters? Raise your hand. Sub-millimeter, under millimeter. Raise your hand. Okay. So we have almost equal answers, equal raising of the hands in all the directions. Now, this is not a complicated math. This is an example of simple math, but I didn't want, of course, you can all do the calculation to check it out, but without doing a calculation, most people would have thought that this x is very tiny. Sometimes they say atomic, much more sub-millimeter and tiny thing. And then one does a simple calculation, which is just like in elementary grade. One learns about the relation between radius and the circumference of a circle. Namely, if you start with the original radius r, you have 2 pi r is the original length of the belt, and you have added 1 meter to it. And that is going to be 2 pi times the new radius, which is r plus this tiny piece x. So if you multiply this out, there's a 2 pi r on both sides of this equation. If you get rid of the 2 pi r, you get that 1 is equal to 2 pi times x. Or in other words, x is 1 meter over 2 pi, which is about 16 centimeters. This is surprising, perhaps, to the mind. And the question is, why did we make this? Why do we think it's small or tiny? And the mistake we make typically, or if we do make that mistake, is that we think in relative terms. We think the amount that is going to be raised compared to the radius of the Earth is tiny. We think in a ratio. That's, of course, very tiny. But it doesn't mean in absolute terms it's tiny. That's all. So our mind is kind of has its own intuition, and in this case, incorrect. But the simple math, simple calculation shows that there's a mistake in that reasoning. But there's more striking fact is this, that if you actually pulled it one side, the height it raised is 121 meters. This one is not simple math. It needs a little bit more detail. You can check it out. It's hard to believe that if you add 1 meter to the circumference and you pull one side, it's more than a half a meter or something. It's actually 121 meters. I will leave that as an exercise for the people who know a little bit calculus, but I just want to, so this is like a little bit more abstract math is needed for this one. But the point is that you can calculate it, and it's in some sense high school math, if you say, or college math, but anyway, it's not too fancy. Other example is based on mathematical continuity and physical laws. Continuity is one of the basic principles of mathematics, topology and all that. But it's also a cornerstone of a lot of physics. We use that in the idea that things do not jump around in physics quite often. So continuity is one of these cherished principles of physics. So I'll try to give some examples of this. Let's go back to the Earth and the equator again. Consider measuring the temperature around the equator. So the temperature, let's assume it's a continuous function, which you would expect it to be the case if the laws of physics are continuous. So as you go around the equator, if you measure the temperature might vary around the circle, around the equator as you're going around. And the question is it necessarily the case that at any moment, 2 points located across the center of the Earth on the 2 opposite sides of the equator, would they necessarily be such 2 points with the same temperature? That's the question. Are there always, at any moment, at least 2 points for which the temperatures are equal in these opposite directions, no matter how the temperature is distributed, as long as it's continuous? How many of you think there are at least 2 such points? Please raise your hand. Wow, everybody knows here. Okay. So, and presumably some of you think it's not, but let me not even ask that question because almost everybody raised their hand. Indeed, this is a beautiful example of power of continuity. You consider the temperature across the reflection points across the circle, across the middle. If you consider the 2 temperatures, consider defining a function which is the difference of the temperatures across in the opposite direction, opposite places. And if this function, which is the difference of these temperatures across the center of the Earth, if this function is 0 anywhere, you're done, because at that point, there will be equal temperatures. So you want to show that this function f has 0 somewhere. And well, suppose it's not 0 and it's positive somewhere. The point is that if you go from one point to the other side, the function flips sign. Because what is one minus the other becomes the opposite itself. So the function goes to minus itself. And when the function goes to minus itself, because of this property, if you go from whatever value to the other value, the function will have to cross 0 somewhere because of continuity, assuming that this function is continuous. So this is a simple application of the continuity to give you such facts. Now, this can be a bit more fancy. For example, you might ask the following question. Can you consider the temperature and pressure on the Earth, on the surface of the Earth, and ask the same question now, not just on the equator, but anywhere on the Earth? Could it be that there are always 2 points which have exactly the same temperature and pressure oppositely located relative to the center of the Earth? Like this. Could it be that temperature and pressure are always the same at opposite points of the Earth? How many think the answer is yes for that? And how many think no? Yes, so this one is a bit more fancy math, but this is also true. And there are, assuming that temperature and pressure vary continuously on the surface of the Earth, there are always at least 2 such points. So here I want to give you a little bit a more abstract example of continuity. This is going to be probably the most abstract example I'm going to say in this talk. So I will apologize ahead of time if some of it is going to be a bit too fast, but let me try anyhow. So gravitational lensing gives an example of continuity. And first I have to tell you what's gravitational lensing. The backdrop of this is Einstein's theory of general relativity, which tells you that if you have light moving in space, if there is matter located somewhere, it will bend the light. And this bending of the light means that light ray does not go in a naive straight line, but in curves, depending on where the matter is located. Once this happens, it's possible that a single object, for example, a galaxy, which is shining light, could get the light from that galaxy to you, can get to your eyes and from 2 completely different paths. This phenomenon is called gravitational lensing because like a lens, it kind of like focuses sometimes. So you could have a situation like this. You have a galaxy. Here we are at Earth. There are some things in the middle. And these lights move around and come to you in 2 different directions. So if you're on the Earth here, you look this direction. Over there, you say, OK, I see a galaxy. And if you look over there, you say, oh, no, I see another galaxy there. You'll be confused about the fact that you think you're looking at 2 different galaxies, but they're the same galaxy. So we can have the same. So if you take a picture of this and you're on the picture of the plate of the picture, you might be confused as spotting 2 different galaxies while you're actually looking at the same galaxy. So for example, in this picture, in this area here, you might think there are all these different objects here. And it turns out that these objects many of them are the same. In fact, in that same area, all these blue circles are the same quasar. And all these 3 orange circles are the same galaxy. So here is a situation, you have 5 images of a quasar, of the same quasar, and 3 images of the same galaxy. This is an actual picture. So it happens, okay? So this is happening. Now, this is a fact. The number of gravitational images that you get, the images that you get like this one, here they have 3 and 5, if no image is blocked, because some image might fall into some dust or something, or a black hole or something. If you ignore that possibility, suppose none of these are blocked, is always odd, or generically, let's say, odd number. And just less than half of these images are flipped. Like they are like left-right asymmetric, not the way they usually see, but some flipped in some form. So for example, if you have 5 images, 2 of them are flipped, and 3 of them are not flipped. Now, this sounds like a deep principle of physics. Now, you should sit down and solve Einstein's equation in detail to figure out, why and why it's odd and so on, and why did it flip and so on. It's very difficult sounding. But actually, this is also as simple as that temperature where everybody almost answered immediately. This follows, again, by continuity argument, so I will try to explain again. why this fact is almost as simple as the other fact, slightly dressed up, basically. And the idea is the following. So this requires a little bit more abstract mathematics, which is what's called the degree of a map. So if you take a map from a space to another space, if you look at a given point on the map and you look at the pre-images, which means the number of the points that went to that point by that function, this is called the pre-image. You can count them, how many pre-images you have for every given point in the image. And the statement is that the net number of pre-images of a given point counted with plus sign if the map is not inverted and minus sign if it is inverted defines the degree of a map. So it's for every map you can do this, and it turns out that for generic points that you choose on the image, this degree doesn't change. So it's a universal number. So you can count it not just for a specific image, but any point on the image, this will have this property. This is a topological mathematical fact. So now, if you look at the Earth, you get like this. You get like one pre-image. Here you might get like 3 pre-images. And here you might get like 5 pre-images. So what is going on here? Here I'm not drawing exactly what the physics corresponds, so I've distorted the picture of the physics to make it look like straight line, even though it's supposed to be bent. So I've undone that bending by bending the circle, around the galaxy. So this is just for illustrative purposes. The point is rather simple. Imagine a sphere around the galaxy and consider a big sphere around, passing by where we are, whose center is the same galaxy. So we have 2 spheres. A sphere both centered at the galaxy, one very close to the galaxy, and the other one passing through us. Every light ray hits the first sphere somewhere, goes some zigzaggy path, and hits the last sphere where we are at some place, assuming it's not blocked. So this path is actually, you can view it as a map. Namely, at each point gets mapped to another point simply by following the light. The light is that map. Is that clear? Now, the pre-image of a given point is exactly the number of images you see. Now, if you go to where you are, you can ask how many different light rays came to me. It's the number of pre-images. Okay, I claim the degree of this map is always 1. Why is that? Well, suppose we get rid of all the matter between the galaxy and where you are. Then, of course, the light ray will not bend or anything. It goes straight out. Then it maps the sphere, the small sphere, to the biggest sphere one by one, point by point. And so, of course, the pre-image of every point is 1 point, and the degree is 1. But that is what if you had turned off all the matter. But now suppose you gradually turn on the matter, increase, build it up from 0, just tiny, tiny, tiny bit, piece by piece, add to it continuously. The degree of the map cannot jump because it's a continuous property. And you're continuously adding this. So the degree of the map, even if you have a complicated galaxy system or whatnot, is still 1. And it gives you this answer. So these kind of arguments, which is kind of power of continuity, can lead to somehow non-trivial statements that sound far-fetched to believe that's that simple. But it's really, underneath of this, just a simple idea. And here, if you can see the plus and minuses, the direction in which you're going around this is flipping depending on which way you're going around the circle, going up or going backwards. It corresponds to orientation reversal. So the number of negative ones is related to that fact. And typically, you get these odd number of them, less than half of them, which are minuses, and just above the half, which are plus. And there are, of course, special points where you get some of these plus and minus come together. Those are degenerate cases. So I'm talking about the generic points of the image. Now I'm going to give you more examples of power of mathematical abstraction. And for this, we need a puzzle about ants. We have 4 ants moving on a plane, going at constant velocity. And these ants collide with each other. We know all of them, except for the 2 of them we do not know if they actually collide or not. So the challenge to you is to answer, will these ants necessarily collide if all the rest collided? So again, I repeat, the ants are moving on the plane with a constant velocity. Their direction is not changing and their speed is not changing, but their directions are all different. None of them are parallel, so they're different. So we'll assume that all these ants are moving in non-parallel directions. Their speed is constant. They pairwise collide, except for two of them where we don't know. Do the last two also have to collide or not? How many think they have to collide? Raise your hand. How many don't think they have to collide? Raise your hand. Okay, roughly I would say half-half. So, yes? No, not at all. First of all, their direction is different. That's why I'm assuming they're not parallel. And their speed, I'm not assuming anything about their speed. Could be whatever speed they have. Okay, so it turns out that you need an abstraction here. You need to abstract from this problem to make it easy. And the abstraction is the same kind of abstraction that Einstein did for this ant problem, that is. Well, namely, you have to think about not just the space, but space and time together. And this is a baby version of some powerful application of thinking about time as part of the space. So we are forgetting about the time here. Let's introduce the time axis into this problem. Think about the two-dimensional sheet where the ants are, and introduce the time. So ants going at a constant velocity translates to the statement that if you trace at every time where the ant is, you get a point at each point, what we call the word line in physics. That line you're going to get is actually a straight line because we are assuming it goes with constant speed. So every ant going down here actually in the terms of space and time corresponds to a word line which is straight line. Is that clear? So when we say that the ants collide, that means they pass at the same point at the same time, which means their word lines collide. So now we have a Euclidean geometry problem. For each ant, we have a straight line. So there are 4 straight lines in a 3-dimensional space, 2-dimensional space like this on one time. And all these 4 lines, out of these 4 lines, each pair intersects at a point, except possibly for 2 lines. Could those 2 lines not intersect is the question. So that's the question. Is that clear? We translate this question to that. So let's see if we can see the picture here. So we first tilt it. We zoom back. We tilt the time. So the ants are actually going in space-time. Now the line 1 and 2 are what we are interested in, the 1 and 2. And the claim is that the 1 and 2 will necessarily collide. And the way you see it, okay, the way you see it is that from this picture, the line 1 intersects line 3 and 4, right? So therefore, 1, 3, 4 forms a plane. The line 2 also intersects 3 and 4, so the 2, 3, 4 also form the same plane. So the line 1 and line 2 are in the same plane. The only way they cannot intersect is if they are parallel, but I assume that they are not parallel. So they have to intersect. So simple geometry. So one of the basic principles we have discovered in physics is called duality symmetries. Duality symmetry is one of the, I would say, most remarkable things that has been discovered. It had been known in different forms before recent years, but in the context of string theory, it has taken a really amplified form. It just basically says that 2 physical systems which look very different could nevertheless be identical. It's like as if somebody's fooling you. It's kind of strange. It actually reminds me of this picture, drawing of Escher. We had this nice exhibit here a year ago or so. So you have this drawing which illustrates an example of duality. So if you look at this drawing, and if I tell you what is this drawing of, if you just looked at the left upper corner, you might have said, well, this is about a day, a sky, and the black birds moving, flying. If you look at the right, upper right, you might have thought that, no, it's nothing to do with the day. It's first of all night, and the white birds are flying, not the black birds. And if you're looking down here, it says there's no bird around. They're just fields, black and white fields, and so on. So this whole thing fits together beautifully into one picture frame. And different corners of it will have a different description. In the physics language, we say this is one description with dual descriptions. On one corner, you have one description, another one, you have a different description, and they fit together. And you can seamlessly go from one picture to another, just like this drawing. This is a typical example of what we see in dualities in physical systems. Oh, so sorry, let me just go back. So I first want to say what the problem is. This is the next puzzle. We have a meter stick, 1 meter long, and we have 20 ants. The ants are going at a constant speed, either to the left or to the right on the meter stick, with a speed 1 centimeter per second. So the meter stick and ants are going 1 centimeter per second. When two ants get together, they collide and then they reverse, they go back. After they collide, they reverse direction, they go back. Until they meet the other ant, and if they meet the next ant, they collide back again and so on. So they go zigzaggy back and forth, depending on how many ants they collide with. Okay, is that clear? Now, unfortunately, the meter stick is finite, and at the end of it, they fall off. They don't die or anything, they just fall off. So usually in my puzzles, I always had somebody dying or something. This is good, they just fall off. The ants are fine. So then the question is, where do you place these ants in order, so you see they collide here, and then they reverse direction, the red hits blue, and then hits and so on. So they go back and forth, and then when they fall down at the end and so on. So the question is, where do you place these ants at the beginning, and which direction you tell them to go in order to maximize the time the last ant falls off the meter stick? Is the question clear? You just want one last ant to survive as long as possible. How many of you think we better put these ants towards the center and go them in opposite direction next to each other, left, right, left, right? How many think that's the answer? Nobody thinks, okay. Okay. How many think that it doesn't matter where you put all the ants except for one? Raise your hand. How many thinks it does matter where you put all the ants, not just one? Raise your hand. Okay. Very good. So, well, this is related to an example, I would say, of duality in the following sense. You see, I put these ants with different colors so you can see their collisions better. But suppose I was looking more faithfully to how the ants look like. Ants are not these colors, right? This is a silly color scheme. Most of the ants are maybe black, maybe. So let's assume that they were black, and let's look at the same thing happening again. What would it look like? Well, do you see them colliding and reversing direction? They are. It's no difference whether they're going through each other or colliding and going back, you see? It's the same, okay? So this is tricking us. In other words, we are doing a duality transformation. Each time they're going back, change the identity of the ant. The net number of the ants doesn't change on where they are. So therefore, this is a simple application of duality, which means that you can imagine the ants go through each other. Well, in that case, it's clear. You just put one ant at the left end, let's say, and instruct it to go to the right. And that's it. You don't care whatever else is going on. Of course, that is not necessarily the ant which makes it to the end of the other side. It definitely isn't. But you don't care. You're just saying one ant will get there at the right time. So that's the power of this duality transformation in this case, to simplify this problem. Now, this is going to be my last puzzle. Okay, I'm almost good in terms of time. And this is probably my most favorite puzzle because it illustrates scientific methodology, how scientists approach science and what we do. So this is the puzzle. We first do examples, or what we call experiments. Then we formulate a general principle based on the results we are seeing in examples. We come up with some kind of a law or some pattern we try to put together out of these different experiments, some kind of a universal law. And then we come up with arguments on why or how it works. Not just the principle, but explain why it's that principle, or why it's working. And so this is kind of what we do. But also, we always go back to the first step again. We still experiment. We never stop experimenting. Science doesn't stop. Okay, so that's a kind of a scientific methodology, and I want to illustrate this. Together, we are going to do some experiment. The experiment we are doing is a bit funny, perhaps. We start with a circle, and the circle has a boundary. A circle is there, and what are we going to do? Well, we're going to choose points on a circle, choose 2 points on a circle, random points, and connect them with a line. Okay, so far so good. How many regions do you get inside the circle? 2, 1, 2, okay. So 2 points gives you 2 regions. Next, we choose another random point, and then connect them together. How many regions do we get now? 4. Needless to say, 1, 2, 3, 4. Okay, 2 points, 2 regions, 3 points, 4 regions. Add another point, connect them together. So you get 4 points, and how many regions do we get now? 8. Good, so you see, you're beginning to see hopefully a pattern. 2 points, 2 regions, 3 points, 4 regions, 4 points, 8 regions. How many of you think 5 points is going to be 16? Raise your hand. How many think it's not 16? Okay, let's do it. So it's 5 points. Let's count. Okay, 16. Okay, so 5 points is 16. Do you see the pattern? Can anyone explain the pattern? Why it's like this? It's kind of like, I don't want to put anybody in the spot, so let me try to explain what one might have thought is the reason. Is that, well, each time you connect 2 points, you divide this region into 2 parts. It's either on the left or on the right, so there's a factor of 2 extra in each such division. And therefore, that's why you're getting a factor of 2 up each time you add an extra point. Okay, we explained the theory. So for 6 points, we're going to get what? How many think it's 32? Raise your hand. Good. So that's 6 points. Okay. 31, sorry about that. It is such a disappointment. We came up with experiments. We came up with a nice theory. We are very sure about it. It sounded good. We had done already a lot of experiments. You know, it's enough experiment. After laborious, you might think I made a mistake. Actually, I did make a mistake originally in one of these numbers, but no, actually, this is correct. I have checked it many times. It's not, it is 31. And this is puzzling. What happened there? Well, the theory was wrong, actually. Our hypothesis was incorrect, and this experiment disproves it, of course. Of course, one has to go back to the drawing board and figure out what the theory is and so on, but this shows already it's wrong. And if you had 7 points, you might have thought, okay, you might ask, you might be itching to know how close is it to 64? Is it 63 maybe? No, it's 57. Okay, so it's getting away further and further away. And you might ask, what is the actual formula for this? Well, this is a case where actually you can mathematically derive the correct formula. It turns out the formula, the number of regions, is given by 1 plus n choose 2 plus n choose 4. It is something which grows with the 4th power of n. And you see up to n equals to, if this continued, n choose 2, n choose 4, n choose 6, etc., it will give you 2 to the n minus 1. So this kind of fools us to behave like exponential or power, but it stops at n choose 4. And why it's this formula, I won't bother explaining it now, but it's not too difficult to show this. So I hope I have conveyed the power of simple mathematical ideas in the context of physics, and many more examples are in the book. Even the most advanced ideas in physics have simple mathematical underpinnings, just like these simple puzzles. Thanks for listening to my talk.
Well, thank you very much for a very entertaining and interesting talk. Any questions or comments? Any puzzles to the speaker? Yes, Sasha.
So the question is the following. Well, do these puzzles and knowledge of these puzzles help to do real physics anyway?
It for sure helps you feel better about physics. But let me tell you actually one thing. When I saw this puzzle about the circle, actually I haven't told you how I got this puzzle. So let me explain how I got this puzzle, just as an example. of how I collect these puzzles. My kids were, one of them is a third grade or something, fourth grade, and comes back home and says, our teacher has given a problem to us. Count the number of regions when you draw a circle and so on. And I said, okay, let's do a few. I did a few, and I said, of course, it's obvious. It's not, 1632. He said, but she says it's not true. I said, oh, come on, your teacher is wrong. So there's that lesson I learned in a hard way. My kids were telling me, third or fourth graders, but it begs us to be more humble when we are so sure about such things. But yeah, so it gives us some humbling lessons, I would say. Another example is that 121 meter. Yeah. I had given this to my class. I was just doing the first version of it, it's 16 centimeters. And one of the mathematical-minded students in the class said I had got a different answer. And I said, what did you get? He said, 121 meters. I said, only mathematicians can give it this answer. And he was right. And it was so shocking to me, I could not believe that it could be such a dramatically large number, and it was correct. So indeed, I think these puzzles sometimes awaken us in terms of being a little bit more careful in some statements.
Yep. All right.
Yes. Well, a good question. Actually, I have been interested in puzzles since I was a kid. And I was hearing these, and as I began learning physics, I kind of said, oh yeah, that puzzle sounds like this thing I'm learning in physics, and this thing is like that thing, and so on. I put them together. My wife was seeing that I'm interested in puzzles and the physics, and she suggested, why didn't you do a course on that? And I said, oh, that's a great idea. So my wife motivated me actually to do the course.
Any more questions or comments? Well, if not, let's thank Cumrun again for a very nice talk.
Thank you.